Okay, and so, well, remember in the last lecture, we spent basically the whole time analyzing the following boundary value problem for the Laplacian on a disk in the plane. And so we're going to remember, we're assuming we have, say, a disk d sub a of radius a, which is centered at the origin in the plane, right? So this is a picture of the domain. And so the problem is to find a function u such that the Laplacian of u is equal to 0 inside the disk, and such that u is equal to a given function h on the boundary, right? And so remember, the idea was, since we have some nice rotational symmetry for this domain, it's helpful to use polar coordinates and to view all these functions as functions of polar coordinates, and in particular use the formula we have for the Laplacian in polar coordinates. And so in this case, remember, well, we can think of the boundary function h as just a function of the angle theta, right? Because the radius parameter is not varying, it's been fixed to be equal to a. And in this case, in order for things to make sense, we want h to be 2 pi periodic, right? And so we saw that under these assumptions, by using separation of variables in r theta, we were able to obtain a Fourier series solution in terms of the parameters r and theta. And then somewhat surprisingly, we were able to actually sum the Fourier series solution and ultimately end up with this integral formula, which tells us that, at least in polar coordinates, the function u of r theta, which is equal to this integral here, solves the problem, right? And so in particular, we can, well, we're always going to be given the function h, which is the boundary function. And so this tells us that we can construct our solution by integrating values of h, which are values along the boundary disk or the boundary circle here, times this other kind of complicated quantity here, and then multiply by this factor, and then we can construct our solution in this manner, right? And so this is a pretty famous formula, which is called the Poisson formula. Right, and it tells you how to solve the Dirichlet boundary value problem for Laplace's equation in a disk in the plane. Right. And so the first thing we want to do today is discuss, well, okay, it's great to have a solution that's in terms of polar coordinates, but for some purposes, it's better to actually not use polar coordinates, but to use x and y coordinates or Cartesian coordinates. And so the question is, well, now that we have this formula, is there a nice way to interpret this formula in terms of Cartesian coordinates or in terms of x and y coordinates? And so there's one kind of obvious way to do this, which is, well, you know how to rewrite r in terms of x and y, and you know how to rewrite theta in terms of x and y, and you can just sort of plug those in all over the place here. But that just seems to make the formula even more complicated, right? So what we want is maybe a way to reinterpret this formula using Cartesian coordinates in such a way that we have a nice formula in those coordinates also, right? And so that's the first thing we want to do here. One thing I do want to mention before we proceed with that is just kind of interpret, like, maybe make a technical observation, like, what do we really mean that this solves the problem with u equal h on the boundary, right? So we mean that the limit as, right, so here notice that inside the domain, inside this disk, right, let's say this is my point inside the disk, this is my radius. R is always in polar coordinates, the interior of the domain is the region where r is bigger than or equal to 0 and also strictly less than a, right? And so we're going to be interpreting the boundary condition in the following sense. Well, the limit as r approaches a of u of r theta is equal to h of theta, right? And so in this sense, this formula solves the boundary value problem, right? And so you can show that, for example, if you assume your function h is maybe continuous on the boundary, that this integral is always well-defined and will always converge as r approaches a to h of theta, right? So notice this is not trivial, because if right, excuse me, sorry. It's not trivial because if r is equal to a, notice that, well, as r approaches a, this is converging to 0, but the denominator of this fraction is converging to something that could potentially be infinite, right? So you have to be a little bit careful. But the details of this argument are written out in the textbook. I think we're going to skip over this in the lecture because I think it distracts a little bit too much from sort of the main points. But I should at least acknowledge that when we say that this solves the problem, we mean in this limiting sense, right? Because I mean, this is really only defined inside the domain. So what do we mean that it's equal to h on the boundary, right? This is the main issue. Okay, and so, right, so let's suppose now that we want to find a good formula in terms of x and y coordinates or in terms of Cartesian coordinates. So how could we do this? Right, so now we want to talk about interpreting the Poisson formula in Cartesian coordinates. And so by Cartesian coordinates, again, I mean like x and y. Right, and so to make this a little bit easier, I'm going to use vector notation. Right, so I'm going to be thinking about points in the plane as vectors. Hopefully you can easily translate back and forth between using like coordinates, like x and y coordinates, and using two-dimensional vectors, right? So we're going to use vector coordinates, or sorry, vector notation. And so let me just copy over the domain again. Let's say this is our domain. Say this is the origin, right? And so this is a circle of radius a, right? And so what I'm going to do is I'm going to let the vector x, which we can think of as the point x comma y using different x's, right? So let this be a point in the interior of the domain. Right. And so maybe this is my my vector x, right? And I'm also going to let x prime be a point on the boundary or a vector on the boundary. Let's say vectors. Right? Right, so let's say maybe this is my, say this is x prime over here, right? And so what I want to do is try to find a way to rewrite the Poisson formula in terms of x and x prime, right? In terms of points on inside points, vectors x inside the domain and vectors x prime on the boundary. Right, and so in order to relate these to the formula, we have to introduce polar coordinates. So suppose, right, my vector x is given by r theta in polar coordinates, and x prime is given by, well, notice that the radius parameter for x prime, since x prime is on the boundary, the length of this vector is always equal to a, right? So this is fixed to be a, and then let me use the angle phi to denote x prime, right? So if we look in this picture, then let's say this is one of the axes here, right? So the angle phi would be this angle here, right, for x prime. And so for this particular picture, for this choice of x, theta is the angle that the vector makes with the horizontal axis. So let's say that that's equal to 0, just for simplicity for now. Right, so let's assume that theta equals 0 for simplicity. We'll see. I'll make some comments about how to consider the more general case later on. Right, and so what we want to do now is come back to this formula and try to interpret this formula using these coordinates. Right. Okay, well, notice that here I have my boundary function h as a function of phi. Well, notice that on the boundary, I know that u is equal to h of phi, right? Well, I'm looking at phi as the angle used to measure x prime in polar coordinates, right? So using polar coordinates, phi is the angle that x prime makes with the horizontal axis. And so we should be able to replace h of phi here by u of x prime, right? So this should be equal to h of phi, right? The only issue is that, right, so this is only in like an intuitive sense. In order to make this precise, you have to worry about the following issue. Well, here we're integrating numbers from 0 to 2 pi, right? Phi is just like a regular integral from 0 to 2 pi, but x prime is a vector, right? Right, and so in order to make this more precise, we have to actually try to interpret this as a line integral, right, along the circle of radius a centered at the origin, right? So I have here x prime is being integrated along this circle, right? We're trying to think of this as values of h as phi ranges from 0 to 2 pi. In order to make this precise, we have to view this integral as a line integral along the boundary of the circle, of the disk, right, which is the circle, right? And so this is what we're going to do. But in order to sort of make this a little bit easier, let's first do some preliminary calculations, and then I'll say a little bit more about that. Well, so notice that just kind of by definition, this r parameter has to be the length of x, and this a parameter has to be the length of x prime. So the length of x is equal to r, and the length of x prime, which is on the boundary, has to be equal to a. And so, well, now what happens if we take the dot product then of x and x prime? Well, remember that you can always calculate the dot product of two vectors by multiplying their lengths times the cosine of the angle between them, right? Where the angle is, like, say this is x prime and this is x, right? Well, in this particular case, we're assuming for now that theta is equal to 0. And so the vector x is along the horizontal axis. And so if x prime makes an angle phi with that axis, then x prime also makes an angle phi with x. And so in this case, well, this is going to simplify to now, well, length of x is r, length of x prime is a, and then we have cosine of phi, right? Because we're assuming that theta is equal to 0 for simplicity for this particular choice of x. Well, this should look familiar because if we come back to this formula, if we set theta equals 0 here, this is exactly what we have, right? Plus these other two factors, a squared plus r squared. Well, this should remind you of some other identities that show up in calculations involving like dot products and lengths of vectors and so on. And so in particular, we'll notice that if we now look not at the dot product of x and x prime, but rather the difference of these two vectors, and we take the length of their difference squared, right? Well, this is equal to the dot product of the difference with itself. Right? And well, we can evaluate this by expanding it out, and you end up with, well, length of x squared plus length of x prime squared minus twice the dot product of x and x prime, right? By expanding this, well, the length of x squared is equal to r squared. The length of x prime squared is equal to a squared. And then we just saw that this dot product is RA times cosine of phi. So I get minus 2 RA cosine of phi. Right? But this is exactly what we have in our integral, right? Right, and so we're going to be able to replace this quantity in the integral by x minus x prime squared, right? And so now we're sort of well on our way to what we're trying to do. Well, we're trying to rewrite this in terms of x and x prime. We know that h of phi should be given by like the values of u at x prime, because x prime is a point along the boundary over here at the bottom of the screen. On the other hand, we know that this quantity in the denominator can be replaced by x minus x prime squared. And then these quantities here are also can naturally be replaced by, right? So r squared can be replaced by absolute value of x squared, right? So now the only issue is worrying about this d phi parameter here. Right, so let me just, in order to make sense of this, let me just quickly review briefly how to calculate the line integral on a circle. Right, so let's suppose that that I have a function of two variables in the plane, right? So let's suppose u function of two variables or function on plane, right? And so, well, right, so the line integral along a circle of radius a centered at the origin, right? So what is the line integral? Well, let's calculate, well, let me just write down the definition, right? So it's defined, well, the notation for this line integral, well, we use the usual integral symbol. Let CA denote the circle, right? So let this be the circle of radius A. Centered at the origin. And so the line integral is the integral along CA of U right? So how do you calculate this? Well, you have to parametrize the circle and then evaluate it along the parametrization. And so let's suppose this is my circle CA, this is the origin. Well, I can parametrize points by, like, say, a times cosine phi times a times sine phi, as phi ranges between 0 and 2 pi, right? And so given this parametrization, I can evaluate my my line integral as now integral in terms of phi from 0 to 2 pi. Let me call this p of phi. Right, this is my p for parametrization. Well, the line integral is given now by, well, I integrate over the range of the parametrization, where now phi is ranging from 0 to 2 pi. I evaluate my function at the parametrization, right? So u of a cosine phi, a sine phi, and then I have to multiply it by the absolute value of the derivative of the parametrization, right, times phi. Well, what is the derivative of the parametrization here? This is the absolute value now of a sine, or minus a sine phi, comma a cosine phi. Right, all I did here was take the derivative of each of these terms respectively, and this is what you end up with. Well, the length of this is equal to a squared sine squared phi plus a squared cosine squared phi to the 1/2, right? Sine squared plus cosine squared of anything is equal to 1. So this is equal to a squared to the 1/2, which is just a, right? And so I can just replace this derivative here. It actually simplifies dramatically in the case of a line integral for a circle to just a, right? And so what this tells us is that the ds this ds quantity that we're using to define the line integral is equal to a times d phi, right? And so I can go back and forth between a line integral in the plane to the parametrized version of the line integral as a function of phi by just multiplying d phi by a and then by changing everything in the corresponding way, right? And so if we come back to the main problem that we're looking at over here, well, I want to interpret this as an integral in the plane or a line integral in the plane. And so I have to replace d phi by a times d phi, and then I'll be able to do that, right? And so now let's actually take advantage of these observations and start plugging everything in, right? Right. So, well, from the Poisson formula, we have u of r theta. Well, now we're viewing r theta as just the vector x, right? And so this is equal to, well, I had a squared minus r squared over 2 pi. Let me just copy the formula and then we'll start plugging in. Right, remember we're assuming that theta is equal to 0 for this example or for this calculation. Right, so let's start plugging this in. Well, let me just leave a by itself because a is a constant. Well, r squared is just the absolute value of x squared, right, divided by 2 pi. And now I want to rewrite this as an integral along CA, where CA is the boundary circle. Right. Well, now in order to do a line integral, I have to replace sorry, I have to replace d phi by 1 over a ds, right? So there's an extra factor 1 over a that's going to show up. Right, and so I'm going to be looking at vector points that are in the circle, right? So x prime is in circle of radius a, centered at the origin. Okay, and now that I'm allowed to use vectors, right? So my function h at vectors on the boundary of the circle is just equal to u at those points, right? So this is just equal to u of x prime, right? And then in the denominator, what do we have? Well, we saw that this quantity is equal to the distance between x and x prime, right? And so this ends up being length of the vector x prime minus the vector x squared, where x prime is on the circle and then x is what I'm plugging in here, right? So this tells us, right? So this is the formula that we end up with. And okay, so this only works when the angle theta is equal to 0, based on what I've said so far, but you can show that actually this is still valid with replacing phi by theta minus phi for any theta. And so the same formula here holds. And so this is kind of a small exercise in trigonometry, which I'm going to leave out of the lecture because it's not too important, and we'll see soon that like kind of the really important special case of this formula that I'm about to talk about. In the formula, in what we're about to discuss, it suffices to take theta equals 0 for now, right? But I do just want to point out that this holds more generally, right, for any theta. Right? It's just slightly more annoying to prove. Right, and so remember that this is interpreted as a line integral along the boundary of the disk. Right, and so the circle CA is the boundary circle. Right. Okay, and so what I want to talk about now are some important consequences. And in particular, we're going to discuss something that called the mean value property of harmonic functions. Right, and so, well, let's set the vector x to be the origin in the above formula. Right, so note that theta equals 0 is okay, right? So if you describe the origin in polar coordinates, you can of course take theta equals 0. So the formula that we have here is valid. Well, therefore we get u of 0, 0. It's equal to, well, notice we had this 1 over a factor. Let me just take that out of the integral. Now I'm setting x equals 0. So I get a squared minus 0 squared over 2 pi a times the line integral on the circle of u of x prime. Right, notice we're setting x equals 0. We're not setting x prime equals 0, divided by length of x prime squared. Right. Well, on this particular, on this circle, the length of x prime is always equal to a. Right, it's just the definition of the circle. It's the set of all points where of length a. So I can replace this quantity by a squared. Right, so this is now equal to, well, I have a squared over 2 pi a. This is just a squared, which I can factor out of the integral because it doesn't depend on x prime anymore. And then I have the line integral on CA of u of x prime. Right. Well, the a squared and the 1 over a squared cancel, so I end up with u of 0, 0, or u at the origin is equal to 1 over 2 pi a times integral of CA of u of x prime ds. Right. And so what does this say? Let's look at this for a second and try to interpret what's going on here. Well, this says that the value, I can recover the value of my solution at the origin by looking at a certain integral of u along the circle, right? So here we have, say the circle of radius a. This is 0, 0. Right? Well, note that the circumference of CA is equal to 2 pi a, right? And so this formula actually says that if I look at 1 over the, well, what is the circumference of the circle? It's the same thing as the length of the circle, right? Right. So if I integrate my solution along the circle of radius a, and then I'm using a line integral, and then I multiply that by 1 over the length, that this gives me the value of u at the origin. And this is for any a. Right? And so what does this say? So this says that u of 0, 0 is equal to, well, what do you get if you integrate a function on a domain and then you divide by the length of that domain? You get the average value, right? So this says that u at the origin is equal to the average value of u along any circle centered at the origin. Right, so this means that the values of u along the circle determine the value at the origin, in the sense that if we average the values along the circle, it gives us the value at the origin, right? And so there's a very special property for harmonic functions, right? This averaging property. Okay, and so this is it's interesting that this is true for the origin, but you may ask, is it only the case for the origin, or does this hold for other points? And actually, we're going to be able to deduce from this formula, along with the translation invariance of the Laplacian, that this is actually true at any point where u is harmonic, as long as, in a suitable sense, as long as it's harmonic everywhere in the disk, right? And so this is what we're going to call the mean value property, right? For harmonic functions. And so this is just going to require a little bit of notational setup, so this is not too confusing. And so I'm going to let say d sub a of x naught, y naught, let this be a disk of radius a, as we've been considering, centered at the point x naught, y naught. Right, and let CA of x naught, y naught be the circle of radius a centered at the same point. Right, and so in particular, CA of x naught, y naught is the boundary of dA of x naught, y naught. Right, so dA is the disk of radius a centered at this point, which includes all the interior points. And then CA is the circle, which is the boundary circle of the domain, right? And so the difference here is that we're not looking at disks centered at the origin anymore. It's an arbitrary point, x naught, y naught, right? And so the theorem is the following, right? So if U is harmonic in this domain, in this disk, then I can recover the value of U at the origin by looking at the average of U along the circle CA, right? So it's 1 over 2 pi A times the line integral on CA of U along these values. There, sorry. Right, and so this is the, sorry. This is the same formula we had up here, except the difference is now I'm allowing any point for the center rather than just the origin, right? Okay, so we're going to prove this in a second, but let me just look at a larger consequence of this result. Right, so let's suppose that D is any open domain. Right, so maybe something like this. Right, so this is our domain D. And suppose U is harmonic in the domain D, right? Meaning Laplacian of U is equal to 0 in D. Well, let's say we pick a particular point in the domain, say x naught, y naught. Well, if we pick a point in this domain, we can always fit some disk, right? That's still inside the domain, right? So if x naught, y naught is inside our domain D, there's some a bigger than 0 such that the disk of radius a centered at this point is contained inside the domain. Right. Well, since we're assuming that U is harmonic at every point in the domain D, it follows that U has to be harmonic at every point in this disk. Right. Right. So Laplacian of U is 0 in this particular disk. But that means that this formula up here applies, right? So the mean value property applies, and we get that U at this point is equal to 1 over 2 pi A times integral on CA of U. Right. And so this says that if you have a quite a general type of domain and U is harmonic in the domain and you fix a point in the domain, then the value of U at that point can be recovered by looking at an average of the values of U along any circle centered at that point, as long as the circle is contained in the domain. Right. And so this works for any A bigger than 0 as long as the disk is contained in the domain. Right. So this says that you have a harmonic function. You can view the values of a harmonic function as the average of the values of any along any circle centered at that point. Right. And so even though everything we've been talking about so far has just been in the domain, special case where your domain is a disk, well, since for a lot of important domains, you can always fit disks inside those domains, like the theory that we're developing here will extend to more general regions. That's kind of the main point here, right? And so later on, we're going to be able to use this property to prove the maximum principle, which we'll see later in the lecture today. But first, let's just return to what we're trying to show here and prove this mean value property, right? Right, and so well, we already know that this is the case for the origin, and so let's prove it now for a general point. Well, what's the idea? Well, we have translation invariance for the Laplacian. But if we shift the coordinates or translate, we can just translate this to the origin. And so we should just be able to obtain this using the formula from above, right? And so that's what we're going to do. Right. Right, so let's do the proof quickly. Right, and so what I'm going to do is, well, I'm going to define a function v of xy. It's going to be my function u from before, but shifted by a little bit. Right, so I'll define the function v of xy to be u of x naught plus y naught. And so what I'm going to do is look at this as a function on the disk of radius a centered at the origin, right? So dA 0, 0. Well, let me just draw that disk here. Right. Well, let's say I pick a particular point, say x or vector x, right? Well, by definition, v at x is going to be equal to u at that point plus x naught comma y naught, right? And so in particular, v at 0, 0 is equal to u of x naught, y naught, right? And so geometrically, what I've done is we've shifted the domain D centered at x naught comma y naught back to the origin. And now we're letting v be sort of like what you get after shifting back to the origin, and you try to look at values of u in this way. Well, it's not too hard to check that the Laplacian of v is equal to 0 in this disk. Right, because at any point in this disk, say this point here, if I calculate the Laplacian at this point, it's the same thing as calculating the Laplacian of u at that point shifted by x naught, y naught. But as soon as I shift by x naught, y naught, now I'm inside the disk of radius a centered at x naught, y naught. And I know that u is harmonic there. And since the Laplacian behaves well with respect to translations, we can see that the Laplacian will be 0. And so you get Laplacian of v is equal to 0 in this domain. Right. So if you don't believe me, if you don't believe what I just said, maybe it would be helpful to just pause the lecture and then just check it. It should be a pretty straightforward calculation to see this. Right, but if this is the case, well then we already saw that we need to have v of 0, 0 is equal to 1 over 2 pi a times line integral on CA of v of x prime. But now let's evaluate this in terms of u, right? So v of 0, 0 we just saw is equal to u of x naught, y naught, right? Because this is what happens if I just replace x equals 0 here, replace x by 0 here. Right? On the other hand, v of x prime, well, this is going to be equal to u of x prime plus x naught, y naught. Sorry, this integral should be over the circle centered at the origin, right? So this is CA of 0, 0, right? And so we end up with, well, u of x naught comma y naught is equal to 1 over 2 pi a times integral along the circle of radius a centered at the origin of u of x prime plus x naught y naught. Right? Well, let's think geometrically what's going on here. We're integrating along this circle values of u at x prime on the circle, but we've shifted by x naught comma y naught, right? So if I take a circle of radius a centered at the origin, and I look at values in that circle, which are what the x prime are, but then I shift all those values by x naught, y naught, well, that's the same thing as just looking at values along the circle centered at x naught, y naught, right? So this is just equal to the integral, or 1 over 2 pi a times the integral along the circle of radius a centered at x naught, y naught of u of x prime ds. Right, and maybe if you want to, maybe so that this is not confusing, let's use a different variable, say z, where z is given by x prime plus x naught, y naught, right? And so this is what we wanted to show, right? And so that's the proof, right? And so it's easy to, it's not too hard to see that if z is in the circle of radius a centered at x naught, y naught, and I define x prime in this way, then x prime is in the circle of radius a centered at the origin, right? Okay. Right, and so again, let's just summarize what this really says. This is kind of a surprising property, which is really only true for harmonic functions, which is like at any point, I can recover the value of my function by looking at the average value of the function along any circle centered at that point, right? I mean, this is why it's called the mean value property, because you have an average value here, right? And so this is true for any a. Right, so this turns out to be a very like kind of a powerful tool when working with harmonic functions. And so what we're going to do now is use this property to prove the maximum principle for harmonic functions, right? So we'll see this as an application. Right, we're going to prove the strong maximum principle for harmonic functions. Right, and let's quickly review like what are we actually trying to show here. Right, so recall the general setup. So we have some domain D, which is connected, meaning it's in one piece. And we're assuming that the Laplacian of u is equal to 0 inside this domain, right? And so we want to show that if we look at the maximum value of the solution, it has to be attained on the boundary. Right? So it's attained only on the boundary of the domain D unless u is constant. Right, so for example, if the function u is equal to 2 at every single point, then of course that function is harmonic, right? Because the Laplacian of a constant is 0. But then the maximum value is just the same at every point, right? The maximum value is attained everywhere. So there's no maximum principle. But what this says is that as soon as we assume that u is non-constant and harmonic, then the maximum value can only be attained along the boundary curve, right? It can't be attained at any point in the interior of the domain, right? And so this is what we want to prove. Okay, and so what we're going to do is, well, let's suppose that the maximum value is attained at a point xm comma ym. Right, so this is the max value. right? And so now let's suppose that this point is inside the interior of the domain, right? So suppose this is not on the boundary, right? Well, we want to see what happens if this is the case, right? How would it be possible for the point where the maximum is attained to be in the interior of the region and not on the boundary, right? So maybe the point is over here. Say this is xm, ym, right? Well, if you think back to our discussion from before, maybe you can kind of see where we're going with this. Well, let's suppose the point is inside the interior of the domain. Well, then I can find a disk centered at that point, which is still contained inside my domain, right? And so, well, then there must be some small parameter a bigger than 0, such that the disk of radius a centered at my point is contained in D, right? This is what it means for it to be an open domain, right? So this has to be an open domain, right? Right, and so you can kind of see here, right? So if my point happened to be on the boundary, this wouldn't be the case, right? Because whenever I draw a circle centered at a point on the boundary, it's never completely contained in the domain. There's always part of the disk that's outside the domain. But as soon as the point is inside the domain, I can always choose my radius small enough that the disk will be always contained, right? Even if I happen to pick a point really close to the boundary but still inside, I could just take a very tiny disk, which will still be inside the domain, right? And so what we do now is we find such a disk for some very small parameter a, right? And let dA of xm, ym be that disk. Well, since this disk is contained in the domain, U is harmonic in this disk. Right? Well, therefore, the mean value property applies, right? So we end up with U of xm comma ym is equal to 1 over 2 pi a times integral along the circumference or the boundary circle of U, right? And so this is equal to the average value of U on the circle. Right. Well, on the left-hand side here, we have U of xm, ym. Remember, this was the point where the maximum is attained. So U is equal to the maximum value here. So we get M is equal to this. And this is true for all A small enough. Right. So maybe to make this a little clearer, let me call this like A star, right? And then this is going to be true as long as like once a disk of radius A star is contained inside the region, then smaller disks centered at the same point are also contained in the region, right? So this is going to be true for any A between 0 and A star. Right. Okay, well, what is this going to actually lead us to? Well, let's analyze this a little further. And so I'm going to make a claim here, which we're going to prove. So the claim is that, well, suppose there's some point, say X star, Y star on the circle CA with U of X star, Y star strictly smaller than the maximum, right? Strictly less than M, right? So maybe this is part of my circle here, and this is the point X star, Y star, right? Well, since U is continuous, that means that if I slightly vary this number, this point along the circle, I'm still going to stay smaller than m, right? So if u is strictly less than m, there's some gap between this value and m. And so if I vary this parameter by a little bit, then u is going to stay smaller than m, right? So there's going to be some neighborhood of the point where u, or some region where u will be smaller than m. Right, so some small region or a small arc on the circle, right? But if u is strictly smaller than m on some small arc on the circle, well, what happens if I look at the average value? Right? I know that u is always less than or equal to m because it's the maximum. And if I have some positive portion of the circle where it's strictly less than m, the average value has to be strictly less than m, right? So the average value would have to be strictly less than m, right? However, if we come back to what we obtained up here, we're going to see that that can happen, right? In fact, the average value has to equal m, right? Right, we just saw that the average value of u on CA is equal to m by using this mean value property, right? And so therefore, well, therefore, what we saw here cannot happen, right? There's no point on the circle where u is strictly smaller than m, right? So therefore, u of xy is equal to m for all points xy on the circle CA, where a is any parameter between 0 and a star, right? Well, let's look at where we are now. So this is the point xm, ym. And so we take a disk centered at this point, right? And so u is identically equal to its maximum at every point on the circle, but it's also true for any smaller circle centered at the same point, right? So here's another, well, I'm not going to get this exact, but here's another circle basically centered at the point. So u has to also equal m here, right? And so as you shrink this parameter a, we're getting a whole family of circles which are shrinking to this point. And at every point on each of these circles, u is equal to m, right? And so therefore it follows that actually u has to equal m at all points inside the disk of radius a centered at xm, ym, right? And so that means that u is constant in the disk, right? dA, sorry. Right, right, and so again, why is this the case? Well, let's pick any point inside this disk, right? This point, any such point, you can eventually find a circle centered at xm, ym such that the point lies on that circle, right? But then just apply the argument that we just applied to see that u has to equal m at that point, right? Right, and so the conclusion, u is constant. Well, let me just copy over what we had here, right? Let me just write it in equal to the max value on this disk, right? Okay, and now let's finish the argument, right? So let's say this is our larger domain D. And so let's say this is the disk that we just say this is xm, ym. Let me draw a disk centered at this point. Let's say this is the dA star of xm, ym. Well, everywhere in this disk, we just showed that u has to be constant, right? well, then in particular, there's another point here where u is also equal to the maximum, right? This is just trivially true because we're assuming it's equal to m at every, we're not assuming, we've shown it's equal to m at every single point in this disk. But then I can find another disk centered at this point, which is also contained inside my region, right? And then just repeat the same argument. Right? And so if we repeat the same argument, we see that u has to be equal to m everywhere in this disk, right? But then notice we've covered a little bit more space, right? So now, well, here's another point where u is equal to m, right? And so once again, I can find a disk centered at this point, which is contained inside my domain, like maybe like this, right? Repeat the argument again, right? And so now u has to be equal to m everywhere here, and we just keep doing this, and eventually we're going to cover the whole domain, right? Right, we eventually cover the domain D, see that u is equal to m everywhere. In D, so u is constant. Right, and so what this says is that the only way the maximum can be attained at a point inside the domain is if u was constant, which is exactly what we were trying to show, right? So let's go back to the statement. We wanted to show that the maximum has to be attained on the boundary unless u is constant, and that's what we just showed, right? And so just to kind of quickly recap the main points of the argument, well, the idea is let's suppose that there's some point inside the domain where the maximum value is attained, right? Well, then I can find a disk that fits inside the larger domain that's centered at that point. And at that point, u is equal to the maximum value m. But then by the mean value property, m has to equal the average value of u along any disk, along any circle centered at that point, right? But the only way the average value can be equal to m, if m is the maximum of the solution, is if u is equal to m at every single point on the circle, right? Because if u is strictly less than m at some point on the circle, then there's some arc where it's strictly less than m, and then you can just calculate that the average has to be smaller than m in that case, right? But that's not the case because we saw using the mean value property that the average has to equal m. And so it follows that u has to be identically equal to m at every single point along the boundary of the circle centered at xm, ym. But this is true for any radius smaller than a certain threshold, right? So at every smaller circle centered at the point, it's also equal to m. And that means it has to be equal to m at every single point in this disk, right? But once we have that, we can choose another point, like say on the edge of the disk, and take another disk centered at that point and keep repeating the argument, right? So we took this point here, and then if I repeat the argument, u has to be identically equal to m at every point here, but then I can take another point here, and then I get a new disk, u has to be equal to m at every point here, and you keep repeating this until you cover the whole domain and see that u has to be constant, right? Okay, and so that's about it for what I wanted to discuss related to applications of the mean value property. And I think that concludes for now, our discussion of harmonic functions. So we were finally able to prove the strong maximum principle.